Okay, ladies and gentlemen, welcome back. Welcome back to vector calculus. Now, in today's lecture, we're going to continue our odyssey into line integrals. Okay? Now, in the previous lecture, we introduced, well, first of all, we motivated the line integral. Then we actually defined it and gave some sort of geometric interpretation to what it was. Today, we're going to look at the applications of line integrals. So, the fundamental application behind line integrals is calculating work done. So, the work exerted by a force on a moving particle over a given curve in a specified direction. Okay, but there are also other very interesting applications of the line integral. Okay, in particular, we're going to look at the so-called flow integral, which measures, for example, a fluid's flow around a curve. We'll also look at circulation, which measures a fluid's flow around a closed curve. Now, circulation should bring back some memories from when we looked at the curl, circulation density. And finally, we'll have a look at flux in the plane. So the flow out of or over a closed curve. Have we seen flux anywhere before? Divergence, flux density. So the big question is there a relationship going on? Well, that'll come in other lectures. So, applications of line integrals. Work. Now, just think back to elementary physics or applied math. The term work refers to the energy expanded when a force is applied to an object to move it along a path. Okay? Now, the most simple situation is when the object is moved along a straight line from between one point and another point by applying a constant force. Okay? Under this very simple scenario, the work is just the tangential component of the force times the distance travelled. Okay, so here's a real simple picture. So here, the particle is getting moved from P to Q. The force, say a constant force, is given by F. And we learned that the work is just the dot product of the force with the vector if we let vector V equal the vector PQ. Okay? So essentially, it's the tangential component, well, I guess it's the component of F in the direction of the vector V times the length of V. Okay, so that's a very simple situation. So a natural question to ask is, A, what happens if the force that's being applied is non-constant? And B, what happens if the particle doesn't necessarily move in a straight line? What happens if it's a curve or a path or something like this? Okay. And the answer is contained in the following. If we move an object around a curved path, curly C, and the applied force is no longer constant, then it seems to make sense to define the work performed by F as the line integral of F over the curve C. Okay? Again, it's basically the integral of the tangential component of f over the curve. Okay. Ah, there we go. That's exactly what I said. Okay, again, I like to make sure that I'm aware that this is a unit vector, unit tangent vector. Okay, again, you can justify that by a slice and sum approach. Well, I'm not going to do it here because I've already done it in previous lectures, so I'll leave that for you to do. All right, so here's a simple example. Calculate the work done by this particular vector field on a particle moving from the origin to 1, 1, 1 along the straight line segment joining the 2 points. Now, this is not a massive leap from the examples we saw in the lecture the other day on line integrals. Okay, all we're doing here is computing a line integral, but it gives us a little bit of extra practice, and also we're seeing how line integrals are used in applied mathematics. All right. So the idea here is the same as a regular line integral. We would parameterize the curve curly C, which is just the straight line segment. And then we would just evaluate f along the line segment, the parameterization, calculate the derivative of our parameterization, dot the two, and integrate. All right. So I'm going to call the origin point A, 1, 1, 1, point B. The first thing is to parameterize. Okay, curly C. So I claim that I can parameterize curly C in the following way. It's just the vector function t between 0 and 1. Okay, now to do that, you can just use the old algorithm. Here, A is the start point and B is the finish point. When I say end point, you know what I mean, right? Okay? Now, the next step we need to do is calculate the derivative of our parameterization. So in this case, we differentiate in a component-wise fashion, and we actually get a constant vector. Now, in general, this will not necessarily be a constant vector, but it's just nice for this example. Third thing we do is we evaluate our given vector field along our parameterization. Okay? So all right. Okay, so if I have a look at my vector field, I replace t with x, I replace x with t, y with t, and z with t. So it's going to be something like t squared, t. So the dot product of f along C with C dash is just t squared t dotted with 1, 1, 1. So we're going to get something like 2t plus t squared there. Okay, so we've done most of the calculations. The last thing we do is integrate 2t plus t squared along our curve. Now to do that, we've got our endpoints here and here, so we just integrate this with respect to t from t equals 0 to t equals 1. Okay, so this is the general way of writing the line integral. But I can break it down in terms of my parameterization. And in this case, it's going to be this integral. Okay, if you work it out, you should get something like 4 on 3 here. Okay, so can anyone suggest how would we interpret a negative answer if we were asked to calculate the work and our line integral was negative? What would the force be doing? Sorry? Yeah, or impeding, I guess, impeding the motion. Here, the force is not impeding the motion. All right, so this is a similar question. We're asked to calculate the work done, but there's a little twist in this one. The twist is that there's 2 subcurves to worry about. Okay? Now, I did talk about this at the end of the last lecture, and I wasn't real happy with the example that I gave. So I'm sort of killing 2 birds with 1 stone here. All right. So here, we're just working in the xy plane, and I can draw or sketch my path using this little diagram. Note the direction. Remember, for line integrals, direction is important. Direction is important. Okay? So now what I have to do is choose parameterizations for C1 and C2, and then I'll separately work out the work over both of these paths, and then add the 2 quantities together. Okay, so here I'm going to let C, curly C, be defined by both C1 and C2. So to parameterize C1, it's just TT. Again, you can use that little algorithm that I showed you before. And for C2, curly C2, again, you can use the algorithm. All right? Notice that there's no change in the x component along C2. The only change is going in y. So if you apply that algorithm, you'll get 1 minus t. Again, you can choose different parameterizations if you want. It's up to you. Just make sure they're tracing out the curve in the correct direction. Okay, the reason I use these simple parameterizations here is that 0 and 1 are easy numbers to work with, right? Okay. So let's calculate the derivatives. C1 dash is going to be 1, 1. And C2 dash is going to be, what, 0 minus 1. So the last thing we need to do is evaluate f along these two parameterizations and then take the necessary, well, the dot products and then integrate. Okay, so f along C1, well, so I go here, x equals t, y equals t, so I sub in here and here. So I'm going to get something like t and t squared. And for f along C2, what am I going to get? Well, I'm going to get x equals 1, y equals 1 minus t. Okay, so we've got all the parts we need. Now we just take the corresponding dot products. Pretty easy. Okay, f C1 of t dotted with C1 dash. What's that going to be? That's going to be t squared dotted with 1, 1. So we get t plus t squared. And doing the other dot product in a similar fashion. So that's going to be 1 minus t squared dotted with, what's it going to be, 0 minus 1, right? So we're going to get something like minus 1 minus t all squared. So all we need to do now is take the two integrals and we should get something like this. Okay, so this integral will be this integral here. Okay. So that's going to be something like 5/6, right? That's from 1 to 0. Okay, what about the other integral? Okay, that's going to be something like this. Okay. So minus 1/3. So to come up with our answer, we add the two integrals together. Okay? Okay, so what are we going to end up with there? A half. Okay, any questions so far? It's quite easy. In fact, it's just mainly going over the line integral properties themselves. Okay, so applications matter, my friends. Let's talk a little bit more about the applications of these wonderful, wonderful line integrals. Okay? Now, there's two ideas to talk about here, so-called flow integrals and circulation. So, suppose that this vector field represents, say, the velocity field of a fluid flowing through some region. So that could be, for example, a turbine chamber. Now, under this circumstance, the integral of this dot product, the tangential component of f, along the curve in the region, gives a measure of the fluid's flow along the curve. Now, let's break that down even further. What it means is, how good of a match is the tangential component of f with the curve? Is there a strong match or not a strong match? Okay, that's basically what it means. Okay, so suppose we have a smooth curve, a nice continuous velocity field f. The flow along the curve from one point to another is just this particular integral here. Now, if the curve is a closed loop like a circle or an ellipse, the flow is called the circulation around the curve. Okay? Now, you can think of, in very simple terms, the circulation is the amount of force that pushes around the curve, okay? The total push when you get from the vector field when going along a path. Okay, so let's do an example. Calculate the circulation of this vector field around the circle with radius A and centre at the origin. And we're going to orient it in an anti-clockwise direction. Okay, so we know which way the unit tangent vector is pointing. Okay, so here's our closed curve. Essentially, we're asked to integrate around that curve, and for that, we need a parameterization. Okay, so a natural parameterization here would be, of course, a cos t, comma, a sin t, right? Okay. Oh, I guess I should parameterize. I seem to switch between English and American English occasionally. Okay, so It's a familiar story now. Calculate the derivative of our parameterization, evaluate the vector field along the parameterization, and take the dot product. Okay, so here's the derivative, and f along our parameterization, what's that going to be? Well, x equals a cos t, y equals a sin t, sub them in here. We're going to get something like minus a sin t, a cos t. Okay, so we've got our necessary elements. Let's dot the two vector functions of interest together and then integrate. Okay, so what have we got here? Yes, a squared. Now, in this case, it's going to break down to a squared sine squared plus a squared sine squared t plus a squared cos squared t, which is just a squared. Now, again, a is a constant here. It is rare that you will get this nice simplification. The dot product is a constant. All right, so finally, we calculate the circulation Okay, so we're happy with that. Nice and simple. Anyone still going? Question? Rob? No, you cool? All right, good. Okay. Did I say that applications matter? Yes. Well, they do. They do. Okay. Well, let me repeat myself. Applications matter. It's the very basis of studying applied math. What is it useful for? This little section looks at the so-called flux. Flux in the plane. When we talk about flux, we mean flow. Flux is the Latin for flow. Okay. If we're investigating, for example, fluid flow, we would like to find the rate at which fluid is entering or leaving a region enclosed by, say, a smooth curve. Okay? Here, I have defined the flux of a vector field across a closed curve. Now, it may be a little bit hard to see on camera, so let me just draw that a little bit bigger. The flux is just the path integral of the normal component of f, where here we have an outward pointing normal. Okay? So we're not talking about tangential components anymore, unit tangential components of f. We're talking about the normal component of f. And we're integrating that component around a closed curve. Okay, so to find the flux, essentially we need to construct an outward pointing unit normal vector, dot that with f, you'll get some function, and integrate that over our closed curve of interest. That's what we do. All right, so how do we do that? calculate the flux of this particular given vector field across the circle in the plane. How do we do that? How do we do that? Well, let's draw a picture. Here's our curve. Now, here I've drawn in an outward pointing unit normal. The question is, what is the representation for this unit normal? It's normal to the curve in the sense that the tangent and the normal, obviously there's going to be an angle of 90 degrees, right? So there's a couple of ways of coming up, at least in this example, with this unit normal. How do we calculate a normal vector to a gradient field? Almost gave it away. To a scalar field. A scalar field, say x squared plus y squared equals 4. What do? Calculate the gradient, right? So calculate the gradient. So you can even move the 4 to the other side. Calculate the gradient. It'll produce a normal vector. It won't necessarily be a unit normal vector, and it won't necessarily be outward pointing. But you can get a unit vector a normal vector by taking the gradient of your curve, the equation for your curve, right? Now, like I said, you do need to be careful. It won't necessarily be a unit vector, and it won't necessarily be outward pointing. Now, for this, the actual outward pointing unit vector is going to be x, comma y, all over root x squared plus y squared. Where did that come from? Well, it's contained in the next slide. Here's a picture of a curve C that is traced out in a clockwise direction. Okay? Now, given the direction, we can always compute the unit tangent with a specified direction. Okay? The question is, if we know that the curve C lies in the plane, we always have this unit vector k, and we can produce this unit tangent vector. Can we use those two vectors to produce an outward pointing normal? And the answer is yes, we can, just by taking the cross product. Okay? If you reverse the orientation, so in this case we have counterclockwise motion, so that the direction of the unit tangent vector is reversed. Yeah, it's still you can still get it through a cross product, this normal vector, unit normal, but you reverse the order. Okay? So let's go back to our problem and see how we solve it. Okay. So I know that my unit tangent is going to look something like that. I can parameterize curly C by something like 2 cos t, 2 sin t, right? So now I can produce a tangent vector just by taking the derivative. Okay? Okay. Now, it doesn't have unit length. So we can make it have unit length though, of course. All right, my parameterization is regular, so I'm not going to be dividing by 0 here. If you divide by the length, you'll get this. Okay, that is the unit tangent vector at any point along the curve, pointing in the direction of motion. Okay, so now what we do is to produce our unit normal, our outward pointing unit normal, we take the cross product of this and the k vector. Okay, so if you expand that cross product, you will get down to the following. Okay? I'll let you expand that cross product. But you will get that. It's a unit vector that is normal to the curve and is outward pointing. Okay, so what do we need here? We need f evaluated along our parameterization, dotted with our outward pointing unit normal. Okay, we want to integrate that around our curve. Okay, so f evaluated along our parameterization is going to be something like this. We're going to get 2 cos t minus 2 sine t, 2 cos t, dotted with cos t sine t. Now, when we expand that, we're going to get some terms cancelling. And we're going to end up with something like 2 cos squared t, according to my calculations. All right. So let's integrate around our curve. Actually, let me start that again. Okay, so now we're integrating the dot product of f with the outward pointing unit vector that's normal to the curve n. So this is along c of t, right? And we multiply this by this. So I guess up here I've sort of abused the notation a little bit. All right, so the length is just it's going to be 2. So the whole thing breaks down to 2 cos squared t times 2 dt. Okay? Now, if you calculate this, it will be something like 4 pi. Okay, so just to clarify, up here, I mean F dotted with the outward pointing unit normal, that evaluated along C of t. Okay? Okay. All right, so you may think, hang on, that was a lot of work. I don't want to do that much work if possible. And the nice thing about this next result is that you could write the previous path integral of f dotted with the unit outward pointing normal in the following form. If f equals mi plus nj, where m and n are functions, then the flux is given by this particular line integral. Now, you can see there that this is given in the differential form, and it greatly simplifies the calculations. Why? Because you do not need to calculate an outward pointing unit normal. Okay? So it simplifies. It simplifies things. Okay, so the big advantage of this is that the tough calculations aren't required. So that's great. We like that. Okay, so where does this formula come from? Where does this formula come from? Well, basically, I'm going to prove to you that this formula holds, and I'm only going to do it for curves that are traced out in the anti-clockwise direction. Okay, so think about curves like that. All right, so as I said before, the unit normal can always be produced by the cross product of the unit tangent vector with the vector k. Okay, we're just working in the plane here, so things are simple. Now, if I think about the unit tangent vector that points in a specified direction, the forward direction, it's just dx dsi plus dy dsj, all crossed with k. Now, if I take this cross product, you should get the following. It's dy dsi minus dx dsj. Okay, so let's take our given vector field and dot it with this normal vector. Okay, now f has components m and n, so if I take the dot product, I'll get something like this. Now, if I take the line integral here, the path integral with respect to arc length, the ds's will cancel out. Okay, so if I integrate this, the ds's will cancel out, and I'll get something like this, which is exactly what is up here. Okay, so that's a brief glimpse at the applications of line integrals, path integrals. The main applications are work done by a vector field, circulation and flow integrals, and flux in the plane. Okay, so have a great afternoon. I'll see you all tomorrow.